Well, a video or so ago, I told you guys that these helical grooves that sit on the back of these pulleys do not pump air. And they don't. That's not an air pump. This is an oil slinger. There are some interesting things that fall out if you consider it to be an air pump. And by interesting, I mean it's just like, it's so easy to show that the people who think this is an air pump really have no idea how things work. But anyway, let me repeat one more time why it is that you know that this thing is not an air pump. If I take this thing and I put it down into the case, and I bring that little ring back around, and then put this thing at about the right depth, it's not that far in, it's about right there. When it gets to the right depth, it does not stick out into the airflow. Since it doesn't stick into the airflow, it's not going to capture any air, so this thing is not an air pump. But like I said, there are lots of people who seem to think that it is an air pump. So why don't we pretend that it is an air pump and see what falls out as far as just the absolute insanity of thinking that it is an air pump. And we can learn a few things, maybe have a laugh or two along the way, at the expense of the people who just don't get it. Well, since this notion of pumping air through the engine through all kinds of means of pumping, let's start with just a generic form. In this particular case, it's going to be engineeringtips.com, engineering forums. Before we go down and we look at this stuff, I want you to understand right now that what we're about ready to read is not engineering, it is mechanic speak. So let's look at the question first. The question is basically about a PCV system, nothing special. We don't have PCV systems, but it's just a generic type of thing. So we come down here to a guy, T. Moose, mechanical, whatever. Let's see what he says. Passenger car engines need ventilation. That is, at one remote region, fresh, clean air comes in that has to migrate through all sections of the crankcase, cylinder head, etc., and then go into the intake to be burned. Just venting off pressure, no fresh air inlet, would leave stagnant regions. First of all, he's simply towing the mechanic company line. You do not need to pass air into the system. If you push air into one piece of the system, there's no guarantee that it's going to flow through the entire system. Okay? This notion that you simply poked a hole, and because I poked the hole, it's going to do what I say that it does. No. The engine and the physics of the engine determine what happens to the flow of stuff through the engine, and you don't need it. Anyway, down here, stagnant regions. I want to investigate the word stagnant. So we go to a dictionary. Stagnant, what does it mean? Well, the one that we're looking for is this right here. It doesn't have inflow, doesn't have outflow. Pretty simple. It's a stagnant region. Nothing goes in, nothing goes out. So let's take a look at what happens if we examine his statement, just venting off pressure would leave stagnant regions. All right, so we looked at the definition of stagnant. So we got stagnant. Let's just write it down here. And stagnant means nothing goes in and nothing goes out. And I always tell you guys, you got to be able to do the math. Well, when you start working in binary languages, zeros and ones, and we start doing things with negations. And the negation symbol typically is listed like this, which means nothing goes in and nothing goes out. What we're looking for is the opposite of stagnant, because the opposite of stagnant is what happens inside your engine. So in order to negate this thing, you take the entire thing and you negate it. Now, in the world of binary, this passing of the negation inside this particular set of braces is something called De Morgan's law. So computer science people should recognize that. Anyway, De Morgan's law tells us that the result of this thing right here is in or out. So that if at some point in my engine I have flow that goes into an area, it's not stagnant. If I have flow that goes out of an area, it's not stagnant. There are no stagnant areas inside your case. It's not possible, but just for the heck of it, just assume that there is a stagnant area inside your case. What that means is that nothing goes in and nothing goes out. So since nothing goes in, that means no blow-by is ever going to get into a stagnant area. Since no stagnant area can have blow-by, then there is no reason to blow out the stagnant area. Therefore, there is no reason to pump air into a stagnant area in order to get the blow-by out. So that guy's argument, his entire thesis is just beyond stupid. However, most mechanics think that it is possible to put blow-by into an area of the engine. That this particular piece here, flow in without anything going out, is possible. And when you have flow into an area with a gas, you have a buildup of pressure. So let's take a look at somebody who was told that they are getting a buildup of pressure and that they need to release it by venting their valve covers. All right, I wanted to take a look at, not the Samba this time, but let's go to a YouTube video. And if you guys watch enough videos, you probably recognize Larson VW. He was putting together a bus and a 66 Beetle, I think, at the time. But anyway, in this particular video, focuses on a problem with crankcase pressure and the breather system, which is pretty much valid to what I'm talking about today. And I watched this video apparently about 2 years ago, and I say, thanks for posting this. Where did you hear this 30 psi crankcase pressure? Because, yeah, believe it or not, some mechanic told him in his research 30 psi. Now, here's what Larson says. I read it while researching the breather problems, so it made perfect sense because oil would ooze out for 20 minutes after parking until I got the breather system. So I want you to focus on two things that are here. One, the 30 psi, and the 20 minutes after parking. We're going to go down to the garage and we're going to do a tiny bit of an experiment. Alright, so I'm going to use this thing right here to do our experiment, right? Obviously I got a couple of gauges. Alright, so I'm going to build up 30 psi in here. And what makes me think that I can use this as a kind of an experimental substitute for that over there? Alright, well, first of all, how do we get pressure inside the canister? Well, inside here there's a one-way valve. You build up high pressure, it pushes through the valve, it goes down into the canister. Over here, what do we do for high pressure? Well, you build it up in your cylinders, and it leaks past the rings. One way past the rings. So I've got one-way valving in here, one-way valving in here. Now, this thing, sitting right there, I've got a valve. That valve doesn't work particularly well, but it will hold 30 psi for a few seconds. What is the difference between this thing, where I've got an exit valve, and that thing? That thing does not have an exit valve. So what we're going to do is build up the 30 psi, and then I'm going to pop the pressure relief valve. The pressure relief valve here is going to blow off the air through that little tiny hole right there, which is about 3/16 of an inch. That's less than half the size of the hole that I've got right there. Now, remember, Mr. Mechanic said we're going to build up 30 psi, and he was able to convince Larson that he was going to have pressure inside his engine from that 30 psi for, what was it, 15 or 20 minutes. So we're going to build up the 30 psi, we're going to pop that valve, and we're going to see how long it takes it to go from 30 down to 0. Let me get it fired up. Alright, we're a little over 30 psi, which I need to do because that thing leaks, and I want to be able to talk for just a second. Alright, first of all, the spring on this relief valve is pretty strong, so I have to use a little bit of leverage on it. When we get to 30, let me see if I can get in really tight so we can see this. I'm going to yank that valve open, and we're going to see how long this takes. Alright, that's pretty darn close to 30 psi. Let's give it a go. And it's gone. Alright, so, do you understand how in the hell Mr. Mechanic can think that there's 30 psi in there and then it's continuing to push oil out the engine for 20 minutes after the engine shuts off? Yeah, I have no idea. You see, the thing is, that hole is smaller than that hole, and I was able to get rid of all that pressure. That was easily less than 5 seconds. You know, it's just insane. Now, keep in mind that I know, because I've read it before, Mr. Mechanic thinks that when the air pressure goes through the rings, once it gets into the case, it has the same pressure. And that's not how it works. Once you're into the case, you are exposed to that gateway right there, which doesn't have a valve on it, which is exposed to atmosphere, or inside the carburetor, less than atmosphere. So, yeah, and Another thing, the idea is that we have to push air in and that we push air in so that the blow-by can come out. I didn't have to push any air in while I was releasing this. We assume that the entire thing is full of blow-by, and the blow-by blows the blow-by out, and that's all that it takes. All right, continuing on with the mechanics theme of you have to push air in order to get the blow-by to come out, we head over to Wikipedia. And I will use Wikipedia all the time. It's usually a really decent resource, and some of what's in this particular crankcase ventilation system write-up is okay. Some of the history stuff is fine, but embedded deep down in here is some massive mechanic speak. So let me run down here and find the mechanic speak. And right there, highlighted in blue, to prevent too much vacuum being created, the blow-by gases are replaced by fresh air using a device called a breather. Now, what's really cool about this is that the guy then is going to transition into some of the history. So let's read the next piece. Another type used of the pressure suction type was used on VW Porsche air-cooled engines, whereby the front crankcase pulley has a reverse screw built into it, which brings air into the engine and escapes the crankcase with the road draft tube. Now keep in mind that my car, it's 1973, newer cars, they didn't have road draft tubes. So there's a pile of nonsense in there, just embedded just from the fact that not all Volkswagens and Porsches had road draft tubes. But let's examine that statement a little bit closer. If you look down here, there's a reference right here. Erwin M. Rosen Peterson Automotive Troubleshooting and Repair Manual. In addition to that, it's also listed right there. So we've got a reference. Generally speaking, that's one of the nice things about Wikipedia is there are references which you can go look up yourself. Let's look it up. That happens to be just a plain old shop repair manual. That's like a Chilton or something like that, apparently. I don't know. But whatever it is, it's written by and for mechanics. That is not an engineering reference. That is not physics. That's not chemistry. That is an invalid reference. That is mechanic speak. Mechanic speak, mechanic speak. Now, maybe this guy had some insight that we don't know about, so we have to look up some of the other things the guy wrote. And we come in right here, Peterson World of Wheels, Peterson Basic Cams, Valves, blah, blah, Ford Book, Body Basic Work, Motor Trend, just some generic stuff for people in general. Surfing? Are you kidding me? What's that got to do with us? And then he gets into some handgun type stuff. So the guy is essentially like a V8 version of a Bob Hoover. Now, we got one other thing we need to look at. All right, this little piece has to do with one of the primary reasons why people want to blow the vapors out. Pump the air in, get rid of the blow-by, get rid of the harmful vapors. Let's read it. This system works very well in getting rid of crankcase vapors, which are harmful to the engine. Let's take a look at what harmful vapors are in there. First thing we got to do is look at the oil. So here's a real nice thing on oil. Notice that this is not an automotive mechanic written. It's not V8, Porsche, Volkswagen. I always tell you this, don't go to Volkswagen and Porsche people like for references. But anyway, they talk about oil. Historically, sulfur was used in lubricating oil formulation chemistry. It has been used as an additive for an antioxidant, part of anti-wear compounding, extreme pressure, enhanced lubricity properties. The oil's ability to lubricate under boundary metal contact conditions. So in oil, there are reasons to put harmful compounds made of sulfur. One of the other things about oil is it doesn't get as hot. At least it's not supposed to get very hot. You try to keep it a little bit cooler so that it stays below the point at which it undergoes thermal breakdown. Above thermal breakdown, maybe some of your sulfur gets released, you get harmful compounds. Keep your oil cool, and these chemicals that are in your oil that typically might contain something harmful like a sulfur, they're there for a reason. It's part of the mixing of the oil. So as far as the oil goes, we don't need to be concerned with harmful vapors. We do, however, need to look at the gasoline. Again, do not go to just a Volkswagen guy. It's good to stay technical. Now, this happens to be a little thing that summarizes how gasolines have progressed and been regulated as far as harmful chemicals through the years. And we need one graph out of this particular paper. And this is the graph. This is for diesels, the part on the bottom, which we aren't concerned with because we got gasoline cars, which is up here in the top. Now, I happen to live in the United States. So there are a whole bunch of other ones that are all listed in here, and you're going to see in just a second that it doesn't really matter so long as you're not from Brazil. But here in the United States, we were allowed to have as much sulfur in our gasolines as you wanted up until about 2004. Then they got regulated. Then in 2006, we got cut back and we were regulated again. And then about 2017, we got cut back all the way to 10. And what does that mean? That means 10 parts per million. So you sit there and you take your gasoline and you split it up into a million pieces. And 10 of those little pieces are going to have some sulfur. 10 out of a million will have sulfur. So basically, the government has already done for you by regulating into the refining processes. Our fuels don't produce harmful vapors. That harmful vapor stuff, remember now, that book was written by a guy in the 1970s. I think the book was 1975. Now, he was likely, either a white-haired old fart or close to a white-haired old fart at that particular point in time. When he was a noob, probably 30 years earlier, 1945, he was being taught by a guy who had the white hair, who learned his stuff back at the dawn of the automobile age, 19-teens, 1920s. So the information that that guy had in his head was already 50 years old, and when he presented it, and it is now presented on Wikipedia, another 50 years later, what you are getting there is 100-year-old information. It was obsolete, basically wrong, factually, when the guy wrote it back in the 70s. In other words, you have to blow air in order to get the air out. That part was wrong. But his part about harmful vapors was in fact correct. There was bad shit back then. But the bad shit has been regulated out. It no longer exists, and it is no longer a reason to pump air into your engine in order to get the bad stuff out. So we don't need to do that anymore. So let's push on. And here we are at his blog site. So, below by. And in here he's got a couple of things that are kind of accurate, but it's full of a bunch of nonsense here and there, and we're really only interested in one piece. Alright, here's what we're talking about pretty much specifically in this video. Its crankcase ventilation system consists of pumping the air in around the pulley hub and using a road draft tube to suck it out. So give credit where credit is due. Any Volkswagen person that you find who's spewing how you have to push air in order to get the blow-by out has most likely visited Bob Hoover's website. If it wasn't his website, then it was word of mouth, or a couple of steps removed. What is that, the Kevin Bacon game or something like that, where you try and find out how far it went between Bob Hoover and whoever the nutbag is who's spewing the Bob Hooverisms. I want to deal specifically with one thing that he has to say about sand sealing the engine. So all modern engines are fitted with shaft seals. Those are crankshaft seals. Any air entering the crankcase is filtered. Yep. Volkswagen owners who like to play in the sand quickly discovered the practicality of such features and began fitting their engine with shaft seals, commonly called sand seal. Continuing on. Sealing the inlet to the VW's crankcase ventilation system dictates the need for an alternative inlet, ideally one that is provided with a filter. Now, there's a couple of bad statements in there. The system does not have an inlet. It's the basic theme that I got to in the prior thing is that screw does not pump air into the system. It dictates the need for an alternative inlet, ideally one that's provided with a filter. Well, you know what? What goes into the crankcase comes past the rings. And what got into the cylinder head came past your air filters. So, yes, he is correct. What goes into the engine as far as blow-by goes did go through a filter. Wow. That's not what he's talking about, but yeah, what goes in went through a filter. Now, what I want to do is look at the following thing that was in his face way back when he was beginning to promote himself as Mr. Grand and Glorious, the late 1960s. And what came out in the 1960s from Volkswagen was something called the Type 4 motor. So let's go look at a Type 4. And here we are, the Type 4 motor. Now, why would I want to go look at the Type 4 motor? Well, it's difficult to see, but you see this big black area right down there? Well, it turns out that is, in fact, a sand seal. It's not called a sand seal on the Type 4 motor. It's just one of their crankshaft main seals. Got a front seal, got a rear seal. But what we want to look at is what did Volkswagen do to put air in order to get the blow-by out? So let's take a look at the valve covers. Alright, we got a pair of valve covers reconditioned, but they're factory. Do you see any bungs and whatnot poking off of it, allowing air to get in and out of the system? Nope. How about some Type 4 heads? Maybe they put the bungs directly into the aluminum Well, there's nothing up in that area, there's nothing over here, there's nothing over there, and there's nothing over there. So Volkswagen was not venting the rocker box. Okay, we still got more holes, right? We can still go and, let's say, pump air out the top of the case. So we look in the back. Holes, holes, holes. No holes. It was a fuel injected motor. Wow, so it didn't have a fuel pump hole over here. Okay, great, fantastic. And this is full of a distributor. So that hole can't be used. So clearly the factory was not pumping air in through some hole in the top of the case. So let's go back to the case itself. You can clearly see right here that there's a lip to hold the seal right there. But yeah, no, there's nothing else happening down there. So let's go back to the main thing. There you go, people. There is nothing input into the Type 4. And Bob made the claim that he looked at the Type 4 and said that all of his Hoover mods were on the Type 4. So if he inspected the Type 4 closely, he would have noticed that the Type 4 violates his pump air in order to get air out of the friggin' crankcase. And unfortunately, you can't blame Bob for that, because I know it's just general mechanic speak that came from decades before he was ever born. And he just picked up on it and didn't have enough brains to understand that it doesn't work that way. But there's even more. Check this one out. In case you didn't know it, Volkswagen enhanced and modified and continuing to develop the Type 1. The Type 1 into a 1.9 and 2.1 liter engines. They were highly modified. But let's take a look at that. They came with valve covers that look like this. No bungs. They came with heads that look like this. You'll see no holes anywhere in there for ventilation. The top of the case, wow, look at that. No holes back in here. That's where the distributor goes. There is a fuel pump hole. So maybe they vented from there. We'll have to check it out. And it's got the standard hole, just like we got on our Type 1s. You can see in here that this particular case has a seal. It's got the little lip in there. And there it is installed into the case. A seal. And what's nice about this photo is you can see the fuel pump block off right there, and it does not have any outlet inlet bullshit going into it. It's just blocked off completely and totally, which means that this engine, and those of you who are familiar with Volkswagen's products, you know what that thing is. That's a water boxer. The water boxer in 1.9 and 2.1 liter iterations, neither of those engines had any inlet type of thing. So again, just like the Type 4, you didn't have to put something in order to get something out. There's even more. Let me continue on. All right, a while back I asked for some help on looking at pulleys through the years, and specifically about the grooves that exist on the pulleys. And I got a little bit of information back, and the information that I got back agrees with the information that I got over here from the Samba. Let me read the important part here. There's two pieces over here that are kind of important. Visually, all the stock ones were the same. So it wasn't like you could easily tell them apart by looking at the grooves. Now, in addition to that, the guy who's doing this stuff here, I'm not going to show his name, but he's not a really big-time poster. But the thing is, the guy's been working on Volkswagens. He's got a shop. He's a shop guy. He's been working on them since 1975. So you got a guy over here that's got like 50 years of experience. And when the guy who's been looking at these pulleys for 50 years says they all look the same. Now remember, I'm only interested in this piece right here, these grooves. When that guy says they all look the same, and all the other information that I've been able to gather says they're all the same, that means they're all the same. This pulley never changed through the years. So let me ask you some questions about these pulleys and, changes through the years. So the idea is that we use this thing to pump air from out here into the case. And is the job of venting air in order to get the blow-by out, is it a constant job? In other words, is a small engine and its blow-by identical to a bigger engine and its blow-by? And the answer is no. See, blow-by is load dependent. A small engine at big throttle is going to have less load on it than a big engine at big throttle. In other words, a 1200 is going to have roughly half the blow-by as a 2300. So you ask yourself the question, if I have something that is load dependent, in other words, a small engine has this much blow-by and a big engine has more blow-by, do you then blow the blow-by out with a mechanism, a pump like this, which does not have the ability to alter its load dependency? In other words, a 1200, a 13, a 15, a 1600 all came from the factory with this very same alleged pump, even though the job the thing had to do was different. Okay, let me ask you another question. Is the amount of blow-by for any particular engine, like for instance my 1745, okay? I'm going up a hill and I got, a nice foot on the gas and I got big throttle setting. So is my blow-by at big throttle setting, let's say 3000 RPM, the same as the blow-by that I'm getting when I've crested the hill and I'm now going down the far side and I've taken my foot off the gas? And the answer is no. And once again, you have an issue where the engine is putting out blow-by in a load-dependent fashion. Lots of blow-by, not much blow-by. And that right there doesn't compensate with a load-dependent throttle setting. It's not load-dependent. So again, this is not an air pump. It can't be an air pump. It can't possibly do the job that it's supposed to do. So to finalize the process of this notion of pumping air in order to get the blow-by out, we actually need to look at blow-by. There's a whole bunch of stuff that we need to look at. First of all, what is stoichiometric? Well, stoichiometric defines this equation right there. This is a chemical equation for burning gasoline, which is basically octane, in oxygen to produce carbon dioxide and water vapor. Now, air-fuel ratio is not oxygen to fuel, it's air to fuel. So we have to go into the natural sciences and look up down here the kinds of materials that make up the atmosphere, which are nitrogen, oxygen, argon, and water vapor, with some teeny tiny trace amounts of a whole bunch of other stuff that we're going to ignore. This gives us our percentage masses, which are going to be important when we move down through the process. So, in order to know that I've done a few things correctly, we take basically a look at the periodic table of the elements, and we have to find out the masses of the oxygens, the carbons, the hydrogens, and come through here and basically come to the conclusion that we have a balanced mass equation. Additionally, since this is 14.7 to 1, I'm going to need that number for my oxygen mass. So, starting with this oxygen mass at 14.7 to 1, we arrive at the following. There's 800 for the oxygen, this much for the nitrogen, there's my argon, there's my hydrogen. But we're burning at 15.7 to 1. That means I'm bringing a little bit more atmosphere in, which means I get more oxygen, more nitrogen, more argon, and a little bit more water vapor. So, utilizing these numbers, the second line right there, we now want to know, what did I put into my combustion chamber? This is the pre-combustion list of what went into the combustion chamber, along with the masses. Notice that we started with the 800 for the oxygen, we increased it, we take that down to here. So we're baselining off of the oxygen. We then use these percentages to back calculate basically the grand total mass, and then the percentages, giving us this much nitrogen, that argon, this much water vapor, and some octane, unburned gasoline. We then fire the system, and we get our post-combustion, which gives us nitrogen, which went through unphased. Nitrogen, generally speaking, doesn't burn. It's a very stable gas. We lose a bunch of the oxygen, which is burned with the carbon to produce carbon dioxide, and burned with the hydrogen from the gasoline to leave us with water vapor. And the argon just went straight through because argon's a noble gas and it doesn't interact with anything. Now, given these particular pieces of stuff, we know from testing, because in that prior video that I did about ventilating the case, I'd done some research, and I know that at most middling RPMs, like highway speeds, about half of your blow-by comes from pre-combustion gases, and about half of it comes from post-combustion gases. So, utilizing these values and this 50-50 mix, I'm going to take 50% of that and 50% of that, add them together, and that becomes our blow-by. Okay, so I finished with this particular sheet up there, And we came up with some numbers. And the numbers show that this is blow-by at an AFR of 15.7 to 1. So what I want to do with these various pieces of blow-by, I'm going to split them into two different pieces that I call A and B. I'm going to take all the oxygen, that goes to A. I take some of the nitrogen and I put it right there. I take the remaining nitrogen, put it right there. I take a little bit of the water vapor, the rest goes down there. I don't want any of the octane, I want none of the carbon dioxide, and I'm going to take a little bit of the argon. Everything else, of course, goes down onto this line right there. I then take this thing right here and I sum the masses up, and it's approximately equal to that number right there. I then sum these masses up. It's about equal to that right there. I've got these things in a spreadsheet, so the spreadsheet's got all the significant digits, and I'm just basically rounding right here. So some of the numbers may not be right, but that's pretty close. Anyway, take the A and divide it by the B, and you end up with a number that is approximately 1, which means about half of the mass is A and half of the mass is B. And the question is, what is A? And if you've been paying attention, you know what A is. Because if I take this number, 1974, and I take that and divide it by this, I get that value, which happens to be the concentration of nitrogen in the atmosphere. I take the oxygen, divide it by that, I get this concentration. I take that water vapor, divided by this, I get that water vapor concentration. And if I take this argon, divided by that number, I get my argon concentration. A is atmosphere. How about that? We are already pumping air into the engine. Well, there you go. That's not an air pump. It can't be an air pump, can't do the job of the air pump. Everything associated with the nonsense of this thing being an air pump is in fact not real. You don't get concentrations of blow-by here and there. You don't get buildups of pressure. You don't get stagnant areas. Everything. You know, if you go over to the Samba, there's plenty of people over at the Samba who recognize that this thing is not an air pump. And I even quote one of the guys over there, I think it's that dude from Australia, Quokka, who said, you know, Bob got a lot of things right, but he got this one wrong. But the point is, as I said, I don't think Bob came up with this thing. This is just a notion that is pervasive from 100 years ago, from a whole bunch of mechanics, from the dawn of these things, internal combustion engines. But again, it's just evidence. Number one, rule number one, you just can't listen to these guys. They don't understand. And number two, in order to understand it, you need to do a little bit of work. In this particular case, usually I say it's math. Well, there's a tiny bit of math. But without the math, you can't do the chemistry, the natural science, none of the physics, none of the engineering. None of it makes any sense unless you can actually do some of that stuff. And what's really going on falls out. Now, if you don't want to do the math and stuff, then you do really have to be able to interpret what somebody like Volkswagen has done with their Type 4 or the water boxer, and you just look at it and you go, okay, what did they do when they advanced the engines past the dawn of the 1920s, 1930s era of what they used to do, and they abandoned this thing? What did they do? What fell out of it? Yeah, anyway, well, that was too much stuff to put into that prior video, so it needed to go under its own separate thing. Those of you who helped me out, thanks, appreciate it, and I will do more later.